Welcome. This is 7.3 Tabular Method for IBP, Integration by Parts. So this is the last little section that we have. Yesterday we studied how to do integration by parts. We found out that if we made like du, start out with dv, integrate to v, that the integration by parts was u times v minus the integral of v du. And sometimes this v du required another integration by parts, so we get u times v minus a new u times v minus the integral of v du. And that process we found could keep happening over and over until we finally had the last integration taken. So what you see here is a lot of u times v, and then a v times du, where we can finally get that integral pass through. So this repetitive nature we will see in the tabular method. All right, let's get it started. We know that we choose like a u times a dv when working tabular, and we still do the same, or doing integration by parts, and we'll still do the same thing. Goodness, slow down. The same thing for tabular method. But there is one restriction on tabular, and that is the fact that what I choose to take the derivative of, my u, I need to have that derivative eventually zero out. So for instance, if I started with an x cubed, it comes down to a 3x squared. Take another derivative, 6x. Take one more derivative, I'm at 6, and take the final derivative, I zero out. Where will this happen? Primarily, what I can think of is an algebraic function, right? Or a polynomial. So for this tabular method to work, you must have an algebraic. Now for the dv, it just has to be something that we can actually integrate so that we can come out with v. And we will take and integrate as many times as it takes to get down to that 0. So if it took me 4 steps in derivatives, I'm going to end up having 4 lines then over on my integral column. Let's give it a shot. Well, this is so fortunate that we have an algebraic function, because that means we can use tabular on it. Let's make this just a little bit more fun and call this 3x up here, okay? Now, this will be my u. I'm going to choose that to be my x squared, and then 2x, 2, and 0. I'm just taking my derivatives on down the line. Then I come over, and this is my dv, and I'm going to choose my dv to be e to the 3x. I need to integrate it 1, 2, 3 times so that I match up with that tabular column from my u. Integrating this, I'll be an e to the 3x times a 1/3 to offset that 3 coming from a chain rule when I took a derivative. The next line, I'll have a new 1/3 times the previous 1/3, giving me a 1/9 e to the 3x. Finally, for my last one, I'll have a 1/27 e to the 3x. To accomplish tabular method, well, we know that this turns out to be u times v minus the integral of v du. We are just replicating this u times v. Okay, and we need to know what signs these are going to be. So what I do is I take this u times this v over here. This was my dv. This would have been my first v then, wouldn't it, when I integrated. So I'm going to do this times this. The sign is positive. So let me just scroll a bit. And it's going to be, well, this is positive, positive, positive. So I'm going to end up with a positive 1. Whoops, that didn't work out. 1/3 x squared e to the 3x. The next line goes to a minus. So on these diagonals, the signs alternate. And I usually just go through and get my signs positive, negative, positive set up. Now I'm going to have positive times positive. That will result in a negative. And it's going to be a 2 times a 1/9, so 2/9 x e to the 3x. Third diagonal here. Looks like we got positive times positive times positive. So we are going to have 2/27 e to the 3x plus some constant. What we should notice is the decline of the degree of x. And that's a pretty good indicator that you've done, some work right. But it is so much faster than doing repetitive integration by parts the old-fashioned way. This accomplishes it in very quick order. All right, the next one, this will be our, let's call this G prime. This I think is going to be my U because it will zero out. And remember, I have to have a zeroing for tabular method to begin correctly. So this will be my U equals x squared minus 5x. My dv starts out with a sign of, do you want to make this, let's make this interesting, 4x, and dx on that. So I take derivatives on this column, 2x minus 5, 2, 0. Same number of steps because we're starting with an x squared. Same number of steps as last time, right? Now I integrate cosine, and that's going to give me negative cosine of 4x. But because I have this 4x, I need to do a correcting factor of 1/4 when I integrate. Then I repeat myself. The integral of negative cosine would be negative sine of 4x, and I allow just a little bit of space. Now I'm going to have a 1/4 times a 1/4, so I'm going to get that 1/16. One more integration. Negative sine, let's call this cosine 4x, and I have 1/16 times a new 1/4, so 1/64. And I think I do just a double check, taking my derivatives. Does it work out each time? It should. And then I feel pretty good about my integrals. Alrighty, connecting diagonals, start with that U, connect it to, because this would have been a V, right? Connect it to that first V. So U times V, U times V, U times V. Plus, minus, plus, and now let's write out our answer. So I have a positive x squared minus 5x times a positive times a negative. So this will turn out to be negative. This will equal negative 1/4. X squared minus 5x needs to be in parentheses cosine 4x. Without parentheses, it would not look correct, would it? I would have had that 5x only multiplying, so you must have your parentheses there. The next one will be a positive, a negative, and a negative. Negative times negative is going to make that positive, and I'll have 1/16 2x minus 5 in parentheses, and I've lost it, sine 4x. One more pass. Well, this 2 is positive. I got the positive sign here and a positive there. We are coming out positive. 2 times the 64th will give us a 32nd. Cosine 4x plus some constant. There we go. That is tabular method. Enjoy it. It is fun, isn't it? You will have a little homework here. Delta Math Part 2. Have a great day.